Understanding Fermi Problems, also known as back-of-the-envelope problems. On Monday morning, 16th of July, 1945, the world's first atomic bomb exploded at White Sands Proving Ground, a desert 60 miles northwest of Alamogordo, New Mexico. About 40 seconds later, the blast's shockwave reached the base camp, where the physicists stood in awe waiting for the results of the explosion. Among the physicists was Enrico Fermi, an Italian physicist who had left Italy in 1938 as fascism was rising and had emigrated to the US. Knowing for his wide knowledge in experimental and theoretical physics, he was serving as the associate director of the laboratory at Los Alamos. In anticipation of the bomb detonation, Fermi had torn a sheet of paper into strips. When he felt the front of the shockwave, he released the strips which were gone by the wind, landing a few yards away. After a brief calculation, Fermi announced that the energy released by the bomb was 10 kilotons of TNT. Instruments had also been placed at the site, which recorded detailed data of the explosion, such as the shockwave's velocity and pressure. Accurate analysis of the data took several weeks to complete, and gave a result of 18.6 kilotons of TNT. Fermi had computed the energy's order of magnitude correctly in just a few moments. The previous story is perhaps the best example of a Fermi problem, and demonstrates the meaning of the term. A Fermi problem is an estimation exercise that uses approximate calculations and logical reasoning to arrive at reasonable answers of a complex, and sometimes a poorly defined question. Most often, Fermi problems rely on order of magnitude arguments and dimensional analysis rather than precise computation. Fermi problems are named after Fermi since he was famous for his ability to make accurate estimates with limited information. They are also called back-of-the-envelope problems since it is claimed that Fermi had a set of envelopes in his suit pocket and he was pulling them out to do calculations on them. Let's solve an easy Fermi problem that requires only some basic information. What is the length of Earth's equator? This question might appear as an impossible one to answer without having key data from a geography or astronomy course. Yet, any person who thinks rationally can answer it without any reliance to any information from any discipline. I will use the size of the U.S. From east to west, the U.S. is about 3,000 miles long. It also has a 3-hour difference between the two sides. As we walk along a parallel that goes through the U.S. and after we return to the initial point, there is a 24-hour difference. This implies that the parallel is 8 times longer than the length of the U.S. and hence about 24,000 miles. However, the U.S. is north to the equator. At higher latitudes, the parallels are shorter than the equator. Therefore, the length must be adjusted accordingly. For the correction, an educated argument can be given using the latitude of a U.S. city, say New Orleans. However, for an approximate calculation, this is not necessary. We can correct the result by 1,000 miles, which assumes an error of about 4%. This gives the length of the equator as 25,000 miles, which can be compared with the actual length of 24,901 miles. Our crude calculation gave a result very close to the real one. Here are some additional Fermi problems. Is there a limit in how tall a skyscraper can be built using standard construction materials? Given the dimensions of Noah's Ark as written in the Bible, could it have been constructed from wood? How many of your atoms once belonged to Julius Caesar? If a high jumper athlete is shrunk 100 times, how high could he jump? From the examples so far, you may have concluded that Fermi problems are for physics and engineering. However, such a conclusion is incorrect. Fermi problems are common in all disciplines. For example, in business for estimating market size, demand, sales, or costs. Example, how many smartphones are sold in a year globally? In marketing for setting goals and planning actions. Example, how many people see an advertisement placed on a billboard of a busy intersection? In ecology for estimating populations or approximating carbon footprints. Example, how many trees are needed to offset a city's carbon dioxide emissions? In everyday life, estimating consumption and wasting, planning resources, or assessing feasibility. Example: how much water does a household use in a month? It is quite common that a candidate is asked relevant Fermi problems in job interviews for highly paid positions. Hence, Fermi problems are a universal tool for developing intuition, fostering creativity, promoting critical thinking, enforcing interdisciplinary connections, and making decisions with incomplete information. They highlight the power of approximation in professional disciplines and real-world situations. A popular application of the Fermi problems is a project that was introduced at the University of Central Florida by Professors Kostas Efthimiou and Ralph Llewellyn, and then continued by Professor Efthimiou over the years, who has presented it in various scientific publications and talks at the meetings of the American Association of Physics Teachers. It is widely known that most non-science students complain that the standard general education science courses have too much science and math for students who really hate these topics. Hence, around 2000, the two professors thought to introduce a new pedagogical approach, which would make students more enthusiastic about studying science. The new approach should contain vehicles of motivation which would be not only familiar to students, but also popular and exciting. And what more popular and exciting could they find than Hollywood films? So, the idea was that instead of presenting the math and physics as a list of dry formulas from a standard textbook, they would present them through Fermi problems and qualitative discussions on the science shown in the movie. This approach ended up in a huge success. It became known as physics in films, and it was replicated by many instructors, publicized by journalists, and used by YouTubers. I will adopt it too, and a lot of these problems will be presented in the videos of this channel soon. Here are some examples. In the movie Armageddon, a large asteroid is in collision course with Earth. NASA decides to send a team of drillers on the asteroid, whose task is to drill a hole on the asteroid, place a nuclear bomb in it, and finally detonate the bomb. After the detonation, the asteroid splits in two pieces which miss Earth. How good is NASA's plan? In the movie Independence Day, an advanced alien species arrives with an immense spaceship. Smaller, but still extremely big, ships are then deployed above every major city on Earth ready to obliterate humanity. However, humans discover the way to destroy these ships and drop them on the ground. Is this victory one worth celebrating for? In the movie Skyscraper, the protagonist jumps from a tall crane to an open window of the skyscraper, although the distance that separates them is large. Is it possible for the protagonist to be successful? In the movie Spider-Man, Spider-Man saves MJ, who is falling from the top of the Queensboro Bridge before she collides with the ground. Did Spider-Man really save her? In the movie Speed 2, a luxury cruise ship collides with a port. The ship's passengers are terrified by the collision as their bodies are subjected to violent forces. Should they really be terrified? Stay tuned, as these and many other Fermi problems will be worked out in this channel. I hope you liked this lecture. If you did, please subscribe to my channel to help the creation of more lectures.